So the electric field vector points in the direction of decreasing electric potential. That's exciting, and that's what that minus sign meant. Now I want to do a little bit of math and clarify a few points regarding the relationship and differences between electric potential, source charges, and the electric potential energy of test charges. To start off, let me remind you of what happens when you work on a charge, specifically. You either change its kinetic energy or you change its potential energy, or both. Let's assume for the moment that the kinetic energy doesn't change, so all of the work that you do, or more correctly, all of the work done on a test charge by an electric field goes to changing the potential energy of that test charge. That means, incidentally, that the test charge moved from a position of some potential to another location in space where the potential was different. So there was a change in potential that the test charge moved from, and as a consequence, got its potential energy changed. And the mechanism that changed the potential energy was the work done by the electric force on the test charge due to the electric field of the source charge. Right. So in math, that simply is the change of potential energy of the source is the negative of the work done, which is F times delta R. Okay. And actually, just to make my math simple, I'm just, instead of calling it delta R, I'm just going to call it R. Okay. It's still a change of position. The reason for that notation is if the electric field through which our test charge moves is the electric field of a point charge, so we'll let capital Q be our test charge, and our electric field be say root Q over R squared. I'm not going to worry about the direction just at present. And we'll assume that Q is a positive point charge, right? Then the force on the test charge is simply Q times V. That's Coulomb's law, which is Q times K root Q over R squared, or K Q root Q over R squared. And of course, you've seen that before. So, the change of potential energy, remember, I should call it delta U instead of just U, but we typically leave delta off unless we really need it. So it's the negative of F times R, the negative of the work done. F is this, A Q over R squared times R. One of the R's divided out, and so the change in potential energy of our test charge is simply minus K Q over R. But KQQ over R, I can write that as Q times negative Q times K Q over R. But the stuff in parentheses is just the potential difference between where the the electric potential difference between the location in space where the test charge started and the location in space where the test charge ended up. In other words, capital B, the electric potential difference between starting and ending points. So that's the connection. Okay. And the minus sign actually isn't really there. If I did this properly with calculus, that minus sign would have vanished. And so the minus sign actually vanishes here. Because what actually happens here is I end up having to do an integral, not just a simple multiplication. And when I do the integration, I pick the negative sign. And so the actual plus sign, don't worry about it, take my word for it. It's positive. But of course, this is a relationship that I developed for you prior. Okay, so this then, although I've written this before, now what I'm trying to make clear is the relationship, what's the difference between the potential energy and the electric potential. This is the change in potential energy of the test charge as it moves from place to place. The reason that it undergoes a change in potential energy is the place that it is moving has an electric field in it, and the electric field has a corresponding electric potential, but the electric field and the electric potential are both properties of the source charge, and it is the source charge, or more correctly, the electric field of the source charge, that is changing the potential energy of the test charge as the test charge moves around. Okay? So the source charge and the test charge are both there, but they are related to each other, but different. You might remember, here's my next point, you might remember from your first quarter of physics that the potential energy actually needs a location in space to be defined as where the potential energy is zero. More than that, you are free to define where your potential energy is zero to be anywhere you want it to be. I haven't said anything really about that yet, but I want to now. Well, since the electric potential and the electric potential energy are so closely related to each other, so closely linked, it follows automatically that, like the potential energy, the electric potential needs a zero. In other words, we need to define a location in space where our electric potential is zero also. Like with potential energy, the choice of where you define V to be zero is arbitrary and will be different in general from problem to problem. A common choice, but not the only choice, is, believe it or not, to define electric potential to be zero at infinity. In other words, when you're infinitely far away from your source charge. Why? Well, it's easy enough. Because look at the expression for the electric potential, where let's see it right here. Notice that as R to the first power, but as R gets larger and larger and larger, the let me look at this. I was pointing at potential energy actually, which was okay, but so V, which is actually a function of R, is K Q over R. So this is V is a function, the electric potential is a function of position. The position is represented by R. Okay, but R is how far away you are from, not from your source charge, but from where you define your zero of electric potential to be located. And notice that as R, I'm sorry, that wasn't, sorry. R is whatever arbitrary location in space you're thinking about, so I'm getting that. So the electric potential at some random location that we'll call R That's what, so R here is wherever you happen to be in space, 2 centimeters or 20 nanometers or 2 light years, or whatever R happens to be. Anyway, so you're calculating the potential at some chosen location in space, call that R. All right, where is the electric potential 0? It's defined to be 0 anywhere you want it to be. The common choice is when R is equal to infinity. Because as you can see, as R increases without limit, this fraction, this calculation right inside, goes to 0. So there you go. So that makes sense. So, in fact, I'll make that a universal rule. Anytime you're dealing with a point charge, and only a point charge now, but anytime you're dealing with a point charge or something with spherical symmetry, like a hollow sphere or solid sphere, hollow spherical shell, whatever, then typically you'll find your 0 electric potential. But there are other charge distributions where you don't do that. For example, I've done this before. 2 parallel plates. One is positive, the other one is negative. It is, in this case, it is common to define your 0 electric potential to be at the negative plate. And then the bottom plate would be at some other voltage, say 5 volts. And by the way, see how this matches up with what I said earlier about the direction of the electric field. Now you know, well, no, let me do it in reverse. If I were to release a positive charge, if I took a positive charge, put it near the positive plate, you know what would happen. It would be repelled by the positively charged metal plate. It would be attracted to the negatively charged plate, and so it would spontaneously fall, if you will, spontaneously move from the positive plate to the negative plate. And so you would move through this distance, delta x. Right? It would do this spontaneously. But I said earlier that the electric field direction is defined to point from high potential to low potential, the direction that a positive charge would spontaneously move. Okay. And that suggests that if I follow that rule, then the electric field, everywhere perpendicular to the lines of electric potential, and it should point like this. And I'm determining the arrowhead direction based on what I just said, that the field should point from high potential to low potential. But, of course, we've talked about this in other contexts, and the electric field vectors in previous lectures, we said, points away from positive charges and point towards negative charges. So the first thing that I told you about the direction that electric field vectors point, and now this new thing tells you what direction electric field vectors should point, they match. I told you field lines point away from positive charges and towards negatives. They do. I told you that field vectors point from high potential to low potential, and they do. See, it matches. Again, the issue is what effect does the electric field, what it have on a positive test charge? And the answers to that is, it causes it to be repelled by positive charges and attracted to negative charges. The other answer is the electric field of a source charge causes a positive test charge to fall from a high potential to a low potential. And by the way, when I talk about falling, I'm talking about falling through a change of potential, not falling in space. So even though it's moving up, I say it falls, but it's falling not from two positions, that one's higher than the other, rather falling from two potentials, and one's higher than the other. And again, the connection between electric potential and electric potential energy, high potential here, low potential here. When the positive test charge is near the positive plate, it has a lot of potential energy. When it gets to the negative plate, it has lost all of its potential energy. So this location in space is this plate is an equipotential of 5 volts. This negative plate is an equipotential that has a value of 0 volts. And there's a potential difference of 5 volts between these 2 points in space. And that's the source charge. After the test charge, it has a certain amount of potential energy here. It has 0 potential energy up here. Why 0 here? Because we defined, and there we are now in a full circle, we defined our 0 of electric potential to be 0. We defined our 0 of electric potential to be at this metal plate. We didn't have to. I could have defined this as 10 volts and this one as 5 volts, and my 0 would have been somewhere else. But why do that? Let's just define it as 0. Okay. Let's do an example. Alpha particle. I think we talked about alpha particles before. Nucleus in a helium atom, 2 protons plus 2 neutrons. We're going to have a couple of metal terminals. So they're basically just going to be poles, metal poles, and metal rods. And one of them is going to be at 6.5 million volts, which is a pretty good potential. And the question we're going to ask is how much potential energy does this thing gain, does the alpha particle gain or lose when it does this? I don't remember if I said it all out loud because I was thinking in my head. Okay, so we have an alpha particle. It starts at one terminal that's maintained at 6.5 million volts relative to another terminal which is at 0 volts by definition. When the alpha particle does this, what happens to its potential? Does it gain potential energy? Does it lose potential energy? And so we have a couple of metal poles. This one will be at the 1, which is 6.5 times 10 to the 6 volts. This one here, B2, which is 0 volts. But that's defined to be. Again, we could have defined our 0 anywhere else we wanted to, but this is convenient, so we'll choose it. And then our alpha particle two protons plus 2 neutrons, starts at rest, goes over here, ends up here. That's an alpha, letter alpha inside that circle that you can read that. And so, what's the corresponding change of potential energy? Okay, so diagram 2, put a coordinate system on here. We're not going to really need a coordinate system, but it's good form. Good. Because you never know when you may need it. But we won't need it here, but I'll put it down here. Anyway, let's say that it starts out at the origin and moves in the x direction. We don't know how far, we don't need to know. We don't have. Pretty solid problem. So we're given two potentials created by the source charges. The source charges are these two electric poles, these two charged metal poles, the electric terminals. We have a potential difference, therefore, V1 and V2. Potential difference between V2 minus V1. The alpha particle is going to move. So the alpha particle has, we were actually asked for potential energy. We know potential, we know the connection, the relationship between electric potential energy of a test charge and the electric potential created by the source charges. And that is U times V. Here, V is the potential difference between the starting and ending points. V2 minus V1. And Q, we know, is going to be 2 times E. Remember that each proton carries a charge of E, charge 1.602 times Coulomb. The neutrons have nothing to do with the problem. So that's pretty easy. That's about it. But before I actually start plugging the numbers and doing the thing, please stop. I'm going to ask a question, and that is the alpha particle, is it going to spontaneously move from the one terminal to the other, or are we going to have to force it? On the recording, answer that question, and we'll come back and we decide on your answer. I'll wait. Okay, you're back. Good. And hopefully you figured out that it's going to move from a high potential to moving, because we're told that it's moving from high potential to low potential. That will happen spontaneously. And therefore, well, that's the answer. It will happen spontaneously. Okay. Moving from high potential to low potential happens spontaneously. Okay, so anyway, Q is 2 times 1.602 times 10 minus 1 Coulomb, 1 proton. The potential difference here is 6. The final potential is 0 volts. The initial potential is 6.5 volts. Okay. And I punched in the numbers and I came out with negative 2.1 times 10 to the negative 12 joules. Okay, I'll let you go through that and yourself. Well, a volt times a Coulomb is a joule. Okay? But here's the thing I want to draw your attention to. Notice the sign of the answer is negative. That tells us that the alpha particle lost that much potential energy, which it shouldn't have done, because it went from high potential to low potential. So a region of space that was at high potential to a location of space that has a low potential, and therefore this positively charged alpha particle lost potential energy as a consequence of that. And that negative sign is your mathematical indication that sure enough it lost energy. So the way you do it is you ask yourself the question before you start plugging in numbers. Do I think that the particle is going to gain energy or lose energy in this process? Figure out the answer to that, and then the sign of your answer had better match your your decision. So that's how that. Cool. The next thing to do is ask, how can we apply these ideas to real, practical, actual electronic equipment? Let's do that next.
Next recording, please.